focus more on what is meant by partition coefficients. Okay, so for partition coefficients, the reason why we use this partition coefficient is basically when you are having two solutions, okay, and if those two solutions are immiscible, okay, they don't mix with each other, they have solution A, solution B. And let's say if you are using a solute, okay, if you are using a solute, it means now if you're talking about solute and solvent, yeah, so please remember solute plus solvent, okay, will give you solution. So to be exact, I think the exact term that I should be using is, let's say, now if you have some simply like this, if this is going to be one particular solvent, okay, let's say solvent A, and this is going to be another solvent, which is going to be solvent B, okay, both of these solvent, they are immiscible with each other, they don't mix. It means they will form two layers. And solute, okay, whatever solute that you use, the solute, they can dissolve, okay, they can dissolve in both A and B. Okay, the solute can dissolve in both A and B. And once they dissolve, okay, because there are two immiscible solvent over there, okay, the solution, whatever things that they are going to form, okay, they are going to actually form something like in equilibrium to each other. Okay, so for example, in this example, they say that if you are using ammonia, and ammonia dissolve in organic solvent and ammonia dissolve in water, and they are going to actually form an equilibrium where you can represent using this equation. They say there is going to be an equilibrium between ammonia in aqueous and ammonia in organic solvent. So this is going to be something something related to further equilibria. So what we can do is, okay, we can actually find out, okay, what is going to be the ratio of the solute, okay, in organic solvent A in comparison to the ratio with the organic solvent, comparison to the solute in water. It means we can actually find a ratio, and that ratio is actually known as partition coefficient. It's like something like your Kc, but now, okay, we are just going to use Kpc, which is going to be Kpc. You can select any of it, okay, but here, let's say I'm going to actually use this equation. So it's ammonia, okay, concentration of ammonia in organic solvent divided by concentration of ammonia in aqueous. Okay, I can just put it like this. So this is going to be called partition coefficient. And this value that we get, okay, will determine something. For example, okay, let's say if you have equal amount of ammonium concentration in organic solvent and in aqueous, you will get the actual value of 1 if it is all equal. Okay, just imagine the concentration is 0.5 here, concentration is 0.5 over here. So 0.5 divided by 0.5 is going to be 1. But now, what happens if you actually get less than 1? Okay, if your value is less than 1, what does it mean? Okay, what does it mean? If it is less than 1 means this value is more, this value is less. It means we can say that if your Kpc is less than 1, we can say that the ammonia dissolve better in water. Okay, the ammonia dissolve better in water because why? There is more ammonia concentration in aqueous. Okay, that is going to be, we can use this value to tell that or to come into a conclusion. So what happens if this value we are getting more than 1, for example? If it is going to be more than 1, okay, that means this value is more, okay, compared to this value. So it means that we can come into conclusion ammonia dissolve more in organic solvent in comparison to ammonia dissolving in water. I think this one is actually something that we need to take note, because they have actually referred to this example here, okay, to actually come into that conclusion. Because I told you, okay, KPC depends on the ratio that you are defining it with. So here, let's say I'll just discuss with you guys with in this question. So here they say that you are going to have a solution of ammonia, and it is going to be 20 degrees Celsius shaken with organic solvent. So it means now, okay, they actually put, okay, let's say we try to replicate this diagram over here. Okay, maybe we can actually use the exact same diagram. Let me erase this. Okay, let's actually use this diagram. So now they say that, okay, 100 cm cube of 0.1 mole solution of ammonia in water. Okay, now imagine this is going to be that 100. Okay, they actually have this. This is going to be 100 cm cube, 0.1 mole per dm cube ammonia. Okay, ammonia. So this is going to be in aqueous. Okay, so after that they put, okay, 50 cm cube of organic solvent. So if this is 100, let's say now I'm going to actually draw maybe here. This is 100. So now this is going to be 50 cm cube, okay, organic solvent. So what we know now is whatever ammonia that you have over here, okay, ignore this part, yeah. So maybe I'll just ignore this part. So it means that I know that um, when I have two immiscible liquid over here, which is going to be water and then organic solvent. Earlier in the organic solvent, there is no ammonia. So all the ammonia is actually coming from the aqueous solution. They will start to actually go up. Okay, they will actually start to go up, and then they will start to be in equilibrium. So there will be some kind of changes that is going to happen. Okay, in related to this. Okay, there will be some changes. So what is going to happen next is we need to find out, okay, we need to find out about what is going to happen next. Is they say that they took, okay, they took 20 cm cube portion. It means now they actually say they are waiting for equilibrium to be established. It means now imagine, okay, you have all this ammonia and so on, equilibrium has been achieved. It means the ammonia that you have over here, they also went over here as well. Okay, they went over there as well. Okay, so they took, okay, they took 20 cm cube of the portion of the aqueous layer. So it means this is the aqueous layer. They took 20 cm cube, not everything. They took 20 cm cube. Just imagine this is the part that is taken. So they took 20 cm cube. Okay, so left with 80 cm cube. Okay, take note. So they took 20 cm cube of the aqueous layer, and then they react with the hydrochloric acid. So let's actually write the equation. Ammonia, okay, when they react with ACl, okay, they are going to actually give you NH4Cl. This is ammonium chloride. And they say that, okay, they took 20 cm cube, 20 cm cube. And then they mentioned that you are titrating it with 0.2 mole per dm cube. And the endpoint, okay, what is endpoint, Shane? Can you tell us what is endpoint?
The end of a reaction, the color.
Yeah, the time that when the indicator changes color. So endpoint is actually similar to equivalence point. Okay, so it means the reaction is complete during the time. Okay, so this one is going to be 9.4. So what we can do is we can calculate the number of moles, okay, of the acid, and then we can replace and actually find out what is the number of moles of ammonia. Okay, what we can do now is we can actually calculate the number of moles of ACl. Number of moles of HCl is going to be 0.2 times 9.4 divided by 1000. Okay, you will get the number of moles of HCl. Okay, can you actually help me to calculate that? Maybe it's hidden over there, but maybe you can just tell me. Once you calculate 9.4 times 0.2, I think you get 1. Okay, according to the slide is there 1.88 times 10 negative 3. Okay, that is the number of moles. Now we can actually say that because 1 mole reacts with 1 mole. Okay, so it means the number of moles, this ammonia in 20 cm cube or 20 cm cube of that ammonia. Okay, they actually have 1.88 times 10 negative 3 moles. Okay, they have that. So what you need to do is you need to change, or you need to actually find out what is the number of moles, okay, that can be found throughout over here. It means in that 100. It means now we only found out in 20 cm cube. So we need to find out for 100. So what we need to do is, if you want to find the number of moles of ammonia here, you need to times it by what, Jody? 20 cm cube. How do you convert to 100 cm cube? 20 cm cube contains 1.88 times 10 negative 3. How about 100 cm cube, Jody?
Find 1 cm cube then times 100.
Yeah, basically you just times by 5. Am I correct?
Yes.
Okay, you times by 5. So you will get the number of moles of ammonia here. So what you need to do, 1.88 times 10 negative 3, you times by 5. And you will get the number of moles here. Okay, which is going to be, if I times by 5, that is 9.4. Okay, I'll write down 9.4 times 10 negative 3. Now, what you can do also is, initially you used to have 100 cm cube of 0.1 mole per dm cube. Initially, when I put it there. But now, after the equilibrium, you only have this amount. So what we can do is, the remaining ammonia should have went to this place. So you can calculate that as well. So let's actually calculate the initial ammonia. Number of moles of NH3 initially. Okay, initial calculation. So the initial calculation is 100 times 0.1 divided by 1000. That is going to be 0.01 moles. Okay, so it means that supposed to have 0.01 moles here, but now you only have 9.4 times 10 to the power of negative 3. So where the rest went? Definitely they went over here. So you can calculate, okay, what is going to be the number of moles of ammonia in organic solvent, equals to 0.01 minus 9.4 times 10 negative 3. And you will get, after you minus, 6 times 10 negative 4. Charlton, can you follow?
Yes.
Okay. So now, all these are not important anymore. So what I do, I'll just erase this part. Okay, so what I have over here now is, I know that this is going to be 9.4 times 10 negative 3 moles of ammonia. And I know here is going to be 6 times 10 negative 4 moles of ammonia. And I know this is going to be in 50 cm cube. Okay, this is 50. And this one is in 100 cm cube. Okay, so these are the information that we have. So the next part is, okay, they need to actually ask, they ask us to calculate the KPC. Okay, what is KPC? Depends on the way that you actually write it down. So let's say now I'm actually going to write it down like this. Let's say here you see solvent A divided by B, or they actually use inorganic solvent divided by aqueous. So let's actually follow the same. You can actually have it the other way also, doesn't matter. Okay, but here let's say since they use that, let's actually use concentration of ammonia in organic solvent divided by concentration of ammonia in aqueous. So this is what I'm going to find. So since we are talking about concentration, okay, so what we need to do is, okay, in organic solvent, this is organic solvent, so 6 times 10 negative 4 divided by, okay, the volume. Okay, the volume is 50 cm cube. You need to change it into dm cube. So 50 divided by 1000. That is going to be the first one, divided by 9.4 times 10 negative 3 divided by 100 cm cube. So 100 divided by 1000. So you calculate. Okay, if you calculate, I think this one will go cancel and so on. So never mind, I can rewrite again. 6 times 10 negative 4 times 1000 divided by 50. And then divided by 9.4 times 10 negative 3 times 1000 divided by 100. 1000 and 1000 will cancel. 6 times 10 negative 4 divided by 50 times, okay, 100, you invert. This is 1, this is 2. Then you calculate 12 times 10 negative 4 divided by 9.4 times 10 negative 3. Help me to calculate. Do you have 0.128?
Yes, sir.
Yeah, so that is actually from the book 0.128. What I want to discuss over here, there is no unit because concentration divided by concentration. So no unit. Now, what I want to discuss over here is about the number. Is this value less than 1 or more than 1? Gabriela, Nicole?
Less.
Less than 1. We obviously use, okay, the organic solvent divide by the aqueous. Yeah, if it is less than 1, it means that this is less, this is more. Okay, so what is the conclusion that we have, Victoria? Ammonia is dissolved more in organic solvent or in aqueous, in water?
In the solvent there.
Because it's actually 0.18 less than 1, it means this is more. Okay, so this is less, so it means that ammonia dissolve more in aqueous compared to organic solvent. That's the meaning. So it means ammonia dissolve more in water. Okay, ammonia dissolve more in water.
So if less than 1, dissolve in water, yes, sir.
Depends on what we are doing, what we are using over here. Like for example, okay, if your KPC equals to concentration of A divided by B, for example, if let's say your KPC, you are getting less than 1. If less than 1 means, of course, the B should be higher. Okay, something divided by something that is higher. This is higher. So it means that the concentration of that solute in B is more. So it means if it is going to be KPC is less than 1, so it means that the solute dissolve more in B. That's a understanding. Yeah. So if it is more than 1, it means the solute dissolve more in A. Okay. So in this case, it depends on how you write the KPC over here. So here we calculated organic solvent divided by aqueous. Okay. So it means if now the value that I calculated is 0.128 is less than 1. If it is less than 1 means this is more. Okay. This is more. This is less. So I can say that ammonia is more in water. It means there's more number of moles of ammonia in that volume of water. So I can say that ammonia dissolves better in water. It means basically there is more ammonia molecule here compared to here. Or you can say this is more concentrated. This is less concentrated. So this is how we use the KPC. So I hope you understand this part. Okay.